All right, so we are moving on to topic 3, volume scaling or changing the dimensions. You might also hear this called changing the attributes. So what's going to happen with this is we are going to be changing either the length, the width, or the height, okay? And this is going to be specifically for rectangular prisms. We're only going to change one of the dimensions, and we're going to see what happens. So if some of you guys do have your Desmos up, that's fine. You can help me with some of the calculations along the way. So in our first example, it just says a rectangular prism has dimensions. The length is 10 centimeters, width is 4 centimeters, and height is 5 centimeters. The first thing we're asked to do is calculate the original volume. So when we do volume of a rectangular prism, we're not doing cylinders right now. It's just length times width times height. So then I could substitute in those values. So my length is 10, my width is 4, and then my height is 5. Does anybody have that calculated, what my volume would be? Should be 200. 10 times 4 times 5. The 4 times 5 is 20, and you multiply the 20 times 10, that gives you 200. So 200 centimeters cubed, because we're dealing with volume. Now we're going to change just one of the dimensions, one of the attributes, and see how that affects your overall volume. So for this first example here, if the height is multiplied by 2, so that means everything else is going to stay the same. So same formula, length times width times height. The length is going to stay 10. The width is going to stay 4. But what will my new height be if it's multiplied by 2? 10. So then what is my new volume if I multiply those numbers? 400 centimeters cubed. Good. Now the blank here, we want to write down what happened to the volume compared to the original. So what would you say happened to the volume if we went from 200 centimeters cubed to 400 centimeters cubed? It doubled. So that's what we're going to put in the blank here. And of course, doubled means you're multiplying by what number? Good. So above that, we'll just write that. Make sure everybody knows what it means. Okay. In our next step here, the next example, we're going to, for the length, multiply it by a half. So that means everything else is the same as the original. So we're going back to the height being what it was originally. The length is multiplied by a half, and the width, again, just stays the same as the original. So you'd have, get this to refocus. Okay. So your formula is the same, length times width times height. Your length is going to be what if it's half of the original? 5. Your width stays 4, that was your original width, and your original height was 5. So those are the values I'm multiplying together. So what is my new volume? 100, good. 100 centimeters cubed. So comparing here's my new volume and my original was up top there. How would I describe like the relationship between the new and the old? It's half of it, right? So we'll say there's two ways you could word this. We could say it's reduced by a half, or you could say what did we divide by if we reduced it by a half? Yeah, so we could say divided by 2. Whatever is easier for you to kind of work with. As long as you know what's happening. right, and then our last part of this example here, if the width is multiplied by 3. So again, we'll say like the length and the height are back to the original, and all we're doing is changing the width. So length times width times height. My original length was 10. My width gets multiplied by 3. So what's my new width? 12, because we started with 4, multiply it by 3, and that's 12. And my height is still the original height, which was 5. What's my new volume? 600 centimeters cubed. Good. What would we say is the relationship between my new and my old? It tripled. Perfect. My volume tripled, which means we multiplied by what number? Good. So we have a few more examples on the second page. By the time we're done with the second page, we're going to try and figure out like a pattern or a rule that we can apply that can save us a little bit of time in the long run. So when you are done with that, just flip over to that second page. Okay. All right, so this says a real world scenario. So all that really means here is it's like instead of saying a rectangular prism, it's giving us a scenario where we would use a rectangular prism. So a company manufactures shipping boxes with an original size of 12 inches by 6 inches by 8 inches. Okay. What word tells us that this is a rectangular prism? Boxes. Dealing with the box, it's a rectangular prism. So that's the only thing like where we've seen some word problems at the bottom of our notes pages the last couple of days, where we did have to pay attention to what words indicated the shape and then what we're solving for. Now this straight up does tell us to solve for the volume, but it didn't tell us in quite such plain terms that we were dealing with a rectangular prism. You have to know that's what a box is. So my original volume, length times width times height. I'm going to substitute in 12 for my length, 6 for my width, and 8 for my height. What is my original volume of this box? 576 inches cubed. And all three of these, we're just going to be changing the width to something different. So next up, what happens if the width is multiplied by 4? So everything else stays the same. Length times width times height. My length is still 12. What is my new width if I multiplied it by 4? 24. And my height is still 8. Okay. What is my new volume? 2,304 inches cubed. Now, these numbers are not as easy to kind of like eyeball, but what happened going from the original to the new? What happened to the volume? Huh? It did get bigger. We want to see how much bigger. It is multiplied by 4, absolutely. So we could say it quadrupled. And I'll just put multiplied by 4 above that. Are you starting to catch on to a pattern? Okay. All right, now we're going to change that width and make it a fourth of the originals, multiplied by 1/4. So length times width times height. My length, still 12. So my original width was 6. Might have to use your calculator for this. What's a fourth of 6? 1.5. It doesn't work out nicely. That's why I said you might want your calculator for that. Okay. And then my height is still 8. What is the new volume? What is it? 144 inches cubed. Good. And we're trying to identify what happened from my original to my new volume. What's the relationship between them? And if you think you figured out the pattern, you could test it with your calculator and see if it works. What do you think happened? It's what? It's fourth. Yeah. It's 1/4 of it. So the way we can word that is we can say it's reduced by 1/4. You could think of that as multiplying by a fourth. Did anybody think of it a different way using division? What would that be the same as? Dividing. It would also be the same as dividing by 4. So whichever way you want to think of it in terms of your pattern, that's fine. They all mean the same thing. All right, and then last, what happens if the width is multiplied by 2? So we're going back to that original width, we're multiplying it by 2. So length times width times height. Length is still 12. My original width was 6, so what's 6 times 2? 12. So my new width is 12 and my height is still 8. So what is my new volume? 1,152 inches cubed. Is that what we got? Okay. So again, what is the relationship between the original and the new one? It's doubled. Good. Which means that we multiplied by 2. Okay. So our conclusion is basically, well, what pattern or what rule did we figure out here? So by scaling one dimension, and by scaling that basically means we're changing one dimension, it directly scales the volume by the, what do you think we might put in those blanks? By the same factor. Basically, yes, it's a scale factor that you're multiplying by, but it directly scales the volume by the same factor.